Hi everyone, my name is Zhu, and today I'm excited to present our work titled Flexible Memory Rotation, Rotated Representation with Dynamical Regularization to Overcome Catastrophic Forgetting in Continual Knowledge Graph Learning. This research is going to present at the Big Data Conference in Washington, D.C., and it addresses a critical challenge in the field of continual learning. In this presentation, I will walk you through the key challenges in graph learning, explain our FMR method in detail, present experimental results demonstrating its effectiveness, and conclude with future direction for this exciting area of research. Let's begin by exploring the challenges in traditional graph learning methods. Before delving into the graph learning, let's first examine the standard pipeline most graph learning methods follow. The process begins with a statistical representation of the graph, where the structure, nodes, and edges are predefined. Models are then designed to capture the relationships within the graph and generate embeddings that represent these components in a Latin space. These embeddings are utilized for various downstream tasks, including knowledge graph completion, node prediction, and graph level prediction. Understanding this pipeline is critical, as it establishes the foundation of how graphs are perceived and used. However, as we will see, this approach has limitations when dealing with dynamical and evolving graphs. This realization has led us to explore dynamical graph learning techniques, particularly in the realm of the continual knowledge graph learning. The previous pipeline assumes that the graph remains unchanged throughout the learning process, which introduces several challenges. First, in real-world scenarios, most graphs evolve dynamically over time. Nodes and edges evolve frequently like social media network, which making statistical graphs outdated quickly. Besides, statistical knowledge graph has temporary limitations. It fails to capture ongoing updates, reducing model relevance. Second, even when adopting dynamical graphs, scalability becomes a significant issue. As the data grows, the graph size grows rapidly, making frequent updates impractical, and it may cause high cost because rebuilding models for each update is inefficient and computationally expensive. Due to these limitations, statistical graphs are not suitable for many practical graph learning tasks. This motivated us to explore continual knowledge graph learning, a dynamical approach that adapts as the graph evolves over time. Since we are talking about the continual knowledge graph learning, this is the example of it. In this example, each snapshot represents the state of the graph at different points in time, highlighting the process of continual growth. G1 shows the initial state of the knowledge graph with a set of nodes and relations. The rest knowledge graphs G2 and G3 illustrates the addition of new nodes and new relations to the existing structure. According to most surveys, we could roughly categorize the continual knowledge graph learning into three types. First one is parameter isolation, protects the model's performance on previous tasks by fully or partially separating the model parameters for each task. Second one is the memory replay. It could prevent forgetting by retraining the model using representative samples from previous tasks. And the last one is regularization based. It expanded terms to restrict drastic changes in most important model parameters. In our method, We propose a novel regularization-based method, but why choose regularization-based approach instead of other types? It was because of these reasons. First is the memory efficiency. It don't require strong per-week task data, making it less memory intensive. Second is the no task-specific parameters. It avoids the need for task-specific parameter allocation, allowing a more streamlined model architecture. Third reason is the scalability. It scales well to a large number of tasks without growing model size or complexity. And the last reason is the effective knowledge retention. By penalizing drastic changes in parameter important for previous tasks, it balances learning new tasks while preserving old knowledge. Building on the advantages of regularization-based methods, our work continues in this direction. However, existing regularization-based approaches has a significant limitation. They rely solely on single-level regularization methods. In contrast, our approach is the first to introduce a dual-level regularization framework. The two levels were referring to parameter-level regularization and graph embedding level regularization. Parameter level regularization assesses the importances of each learnable parameter to stabilize training. Graph embedding level regularization evaluates the significance of each node or relation to ensure robust embeddings. Without parameter level regularization, models treat all learnable parameters equally, failing to prioritize the most important ones while also assigning undue weight to less significant parameters. Similarly, without graph embedding level regularization, models are unable to identify which nodes or edges hold greater importance within a knowledge graph, limiting their ability to unlock the full potential of the graph. By integrating these two levels of regularization, our approach effectively overcomes these limitations, significantly improves model performance and adaptability. To achieve this, we propose a novel regularization-based framework called Flexible Memory Rotation, in short, FMR. The way we implemented parameter-level regularization is applying the future information matrix we called FIM to construct the weighting matrix in each snapshot. FIM is particularly effective at assessing the contribution of individual parameters, making it a natural choice of evaluating parameter importances. But FIM assumes the independence between two snapshots, which does not hold in our case, because the growing knowledge graphs are involved to the previous knowledge graph. So, we propose to use a vector rotation technique to foster independence. For the graph embedding level regularization, we implemented a dynamical embedding width. This width leverages the frequency of nodes and edges to evaluate their importances, enable the model to focus on the most significant components of the knowledge graph. This is the figure. It illustrates the normalized future information matrix of the relation embeddings across 5 snapshots for 4 datasets, highlighting how FIM values changes before and after applying rotations. In these comparisons, EWC represents the model that utilizes the FIM without rotation, while our approach incorporates the FIM with parameter rotation. In the EWC plots, visible diagonal lines indicate strong dependencies between snapshots, indicating interference across the different time steps. In contrast, our methods effectively eliminates these inter-snapshot dependencies, as evident by the absence of diagonal lines, ensuring a higher degree of the independence between snapshots. In our approach, we satisfy the independence assumption by employing a rotation techniques like a REWC. This is a concept widely used in continual learning. However, existing rotation methods are not directly applicable to knowledge graphs, so we developed a customized reparameterization approach. This is the figure of our customized reparameterization approach. It shows the reparameterization process of embedding space within a knowledge graph. It shows how entity and relation embeddings at a given snapshot are transferred into rotated entity embedding space and rotated relation embedding space, respectively. With embedding rotation, using rotated parameter instead of the original learnable parameter to update a FIM. This is the model overview. Given a knowledge graph at time I, the initial embeddings, E initial, are processed through a masked autoencoder to produce the intermediate embeddings, E inter. These embeddings are then used in the translational model to make predictions. At the same time, regularization is applied to the embeddings to preserve prior knowledge and prevent forgetting of the previously learned information. The resulting trait embeddings, E trait, are then used as the initial embedding E initial for the knowledge graph at the next time step, I+1. The overall model incorporates the three key loss components. The translational loss was divided from the translational model. This loss ensures the proper arrangement and the consistency of embeddings within the knowledge graph. Regularization loss originating from the regularization mechanism. This loss penalizes drastic changes in important parameters, preserving stability across tasks. MAE loss sourced from the masked autoencoder. This loss focuses on the reconstructing masked embeddings, enhancing the model's ability to learn meaningful representations. We conducted extensive experiments on 4 benchmark datasets, comparing our approach against the 12 competitive models designed for continual learning. These models are grouped into the following categories. The first one was the baseline models. This group represents different training strategies. First one is the retree, which is the joint training. It constantly delivers the best performance, but demands the highest computational cost. The snapshot only trained on the most recent snapshot, neglecting prior knowledge. The fine-tune model applies the basic fine-tuning without additional mechanism for continual learning, resulting in limited adaptability. Second group is the inductive models. This category includes advanced knowledge graph models like MEAN and LAN. The third group is the parameter isolations, include the PNN and CWR. Also, following with the memory replay-based models like GEM and EMR. The last group was the regularization-based methods. This group includes the SIEWC and LKGE. Our results demonstrate that FMR significantly outperforms existing continual knowledge graph models. Notably, on the FAC dataset, FMR even superpowers the joint training, showcasing its ability to balance efficiency, adaptability, and performance. After the experiments, we did the result analysis. This is the performance comparison of our models and the EWC models across 5 snapshots for 4 datasets. Each subgraph represents the MRR value for each model at a given snapshot test set. The deeper red color indicates a higher MRR, while a shift towards blue signifies a lower MRR. Notably, it constantly achieves higher MRR values, with significant peaks observed in the entity and hybrid datasets. This performance underscores its effectiveness in retraining and utilizing previously learned knowledge even as it adapts to new data. A critical advantage in dynamic learning environments where models undergo sequence training on well-learned datasets. In summary, compared to the EWC model, our model not only preserved the old knowledge, but also achieved better performance in the new knowledge. This figure illustrates the knowledge transfer for well-learned models across 4 datasets. Bars represent FWT and BWT values. FWT is defined as the impact that learning a task has on the performance of future tasks. BWT quantifies the impact that acquiring new information has on the retention of previously learned tasks. As shown in the figure, our model achieves a BWT value close to 0, indicating minimal forgetting of prior knowledge. This exceptional retention performance highlights our model's superiority over others in managing continual knowledge graph learning challenges. In our application study, represented in this table, we explored the effects of using embedding transfer, masked autoencoding, and regularization on the performance of link prediction across 4 datasets. We summarize the impact of each component. UET improves the adaptability and accelerates the convergence, particularly in the relation and hybrid datasets. Removing MAE significantly lower performance, highlighting its role in refining representation and accuracy. Regularization is critical, especially in relation, showing its importance in balancing and old knowledge. In this paper, we represent the FMR model, which employs a dual-level regularization strategy to effectively address catastrophic forgetting in continual knowledge graph learning. Our approach uniquely combines the cross-grained rotational adjustment of the parameter space with fine-grained embedding optimization. For future work, we aim to refine our approach by developing more efficiency methods to assess the quality of old knowledge, focusing on retaining only on most useful information in subsequent snapshot. This is our reference that we used in this slide. If you have any questions, please feel free to email to me. Thank you for everyone.